MALDI TOF mass spectrometry is a versatile analytical technique to detect and characterize mixtures of organic molecules, especially large synthetic polymers and biopolymers. MALDI stands for Matrix-Assisted Laser Desorption Ionization. This ionization method involves a laser striking a matrix of small organic molecules to make the large, fragile analyte molecules into gaseous ions without fragmenting or decomposing them. TOF stands for time of flight, a mass spectrometry method that separates ions by their mass-to-charge ratio and determines that mass-to-charge ratio by the time it takes for the ions to reach a detector. Let's look at each of these components of MALDI TOF spectrometry in detail. Like any form of mass spectrometry, the MALDI TOF process first involves ionization of the analyte molecule. The analyte is the molecule or mixture that's being analyzed.
MALDI is very versatile, and basically if you can put a charge on it, you can look at it. We can look at things that are very small. We can look at lipids. We can look at peptides. So it really gives you a very nice range.
MALDI TOF is best suited to analyzing biomolecules like peptides, lipids, nucleotides, saccharides, or other organic macromolecules. Because they're so large and can decompose when heated, traditional ionization techniques like electron impact will fragment or destroy macromolecules. MALDI is considered a soft ionizing technique that ionizes analyte molecules whole. Key to the MALDI ionization process is the use of a matrix. The matrix is a small organic molecule used to facilitate the ionization process. A few common examples are shown here, such as CHCA, DHB, and SA. Common to all matrix molecules is a conjugated pi system, like a benzene ring and attached functional groups. This conjugated pi system is able to absorb energy in the form of UV light and blast the analyte molecules into the gas phase. Solutions of the matrix and analyte are deposited onto a sample plate known as the target. The target can be made of polished or ground stainless steel and has spots for several different samples to be applied. The solvent is allowed to evaporate from the sample solution, leaving behind a solid sample spot on the target that will be analyzed by the MALDI TOF spectrometer. Once inside the spectrometer, the target is brought into a vacuum and struck by a pulsed UV laser, usually at a wavelength of 337 nanometers. The laser energy is absorbed by the matrix molecules, which are energetically ablated from the surface of the sample, carrying the analyte molecules into the gas phase as well. During the ablation process, the analyte molecules are ionized, usually by proton transfer with the nearby matrix molecules. The most common MALDI ionization format is for analyte molecules to carry a single positive charge. Now that the gas phase analyte ions have been generated, their masses can be analyzed by the time of flight mass spectrometer. The time of flight process accelerates the gas phase ions in a high voltage electric field. This field imparts a constant amount of kinetic energy on the ions. Because kinetic energy is equal to 1/2 mass velocity squared, a constant kinetic energy will cause the smallest of the ions to travel the fastest. In this example, we have a mixture of 3 macromolecules with masses of 1, 2, and 4 kilodaltons, where 1 kilodalton equals 1,000 atomic mass units. Using standard TOF conditions, this would cause the smaller 1 kilodalton ion to be accelerated to the fastest velocity, around 54 kilometers per second. The 2 kilodalton ion would be accelerated to around 38 kilometers per second, and the largest 4 kilodalton ion would be accelerated to the slowest velocity, around 27 kilometers per second. The TOF detector then records the time it takes for the groups of ions to travel a certain distance. From our previous examples, for a standard 1.5 meter flight, the smallest ion would reach the detector in around 28 microseconds, the next at around 39 microseconds, and the largest ion in around 56 microseconds. From these times, and the known constant kinetic energy of the electric field, the spectrometer is able to calculate and record the mass-to-charge ratio of each ion it detects. MALDI offers a number of advantages over other forms of ionization, such as electron impact. The most important advantage is the fact that large organic molecules, such as synthetic and biopolymers, simply cannot be brought into the gas phase and ionized by conventional gas chromatography. The relatively recent introduction of MALDI and electrospray ionization has allowed for the study of molecules that were previously too large, polar, or otherwise non-volatile to be ionized in the gas phase. MALDI is considered a soft ionization method, meaning the complete molecular ions remain intact when ionized. Harsher ionization, like electron impact, can cause the molecules to fragment. This soft ionization makes the direct mass spectrometry of mixed samples possible. When only the molecular ions are observed, the mass spectrum shows the distribution of the different particles in the sample, arranged by their mass-to-charge ratio. For mixed samples with fragmented ions, the overlapping fragment masses would make identification of the individual components very difficult. Because there's no heated injection chamber, like in other forms of ionization, MALDI allows for the analysis of sensitive molecules that would decompose under high temperatures. Finally, MALDI allows for the preparation and storage of a solid sample. Because the solvent is allowed to evaporate from the matrix analyte sample solution, a solid sample spot is left behind on the target plate.
So you basically are only shining the laser light on a very small percentage of your sample, which means you've got a lot of sample left over if you want to go back to that sample. These plates, they can be archived, they can be stored under nitrogen or argon, and people have gotten pretty decent results waiting a couple of weeks.
MALDI offers versatile molecular analysis with broad-ranging applications.
There's really no limit to who might use MALDI. So there's the traditional path of a chemist or a biochemist looking to, study some compounds using MALDI. There are molecular biologists using MALDI to study DNA, or maybe RNA, or maybe RNA protein conjugates. But beyond that, there are the food scientists who are trying to study allergens in materials, or think about sectioning a cancerous part of the brain and actually trying to determine what the profile of that cancer is. How dangerous is that cancer? Is it benign? Is it aggressive? So that's just one of these burgeoning areas that I expect us to see a lot more applications in.